I'm interested in making this a clockable delay, so I've knocked up a little circuit here that lets me take an external clock signal and feed it into one of the pins of the Pico, clamping it to +3 volts, because this could waggle, up and down from -10 to +10 volts, I guess, in Eurorack land. I'm going to feed the external clock in here, as good as anywhere, and then I need to be able to choose my multiplication or division of the external clock frequency. So I figured a 4-way BCD binary coded decimal switch would give me 16 possible multipliers or dividers, and I'm going to feed that in there, so I've got to find a suitable BCD switch. Jump back into the code briefly. This is where I'm setting up the GPIO input for the external clock input, and this is where I'm setting up the 4 GPIO pins for the incoming divisor. This is the external clock interrupt triggered on a rising edge, so I don't care really what the incoming waveform looks like, particularly what its duty cycle is, so long as I'm getting regular rising edge pulses. And I'm calculating the external clock period by using the internal Pico's microsecond timer, so that gives me the number of microseconds between each clock pulse. I'm then running it through a moving average buffer. This is just so that I can smooth out little bits of jitter from the external clock signal, and I'm noting the phase and waggling the incoming LED. This is the function that reads the BCD switch, so I've called it update divisor, and because I'm using consecutive GPIO pins, I'm using GPIO pins 2 through 5, I can just read all the GPIO pins, shift them right 2 bits, blank off everything apart from the lower 4 bits, and that gives me a divisor in the range of 0 to F. And then I'm reading the current divisor from an array of 16 possible divisors. Just show you that. Here they are. It's an array of 16 floats, and because of the way the BCD switch works, far round clockwise to the right is the 0, which is 12, so it actually comes after the 8 there. But I'm dividing by 1, multiplying by a half, a third, a quarter, a fifth, a sixth, an eighth, a 12th, and a 16th. And those are my delay multipliers. This is where I'm calculating my global delay. So I'm taking the external clock period, dividing it by the sample length, which, because we're sampling 48 kilohertz stereo, that's 96,000 samples per second. That gives me each sample's 10.41 milliseconds long, and I'm multiplying that by that divisor that we read. So the global delay will be some multiple of the external clock period. This is where I'm processing the audio. So the read pointer needs to lag behind the write pointer, and it's going to lag behind by that global delay figure times 4, and times 4 because we got 4 8-bit bytes per 32-bit sample. So just to make the maths simple, I'm adding the length of the buffer and taking off the global delay, and then ANDing it with 3F, which wraps it conveniently at the end of the buffer. So I'm taking in an external clock signal. This is my little transistor circuit that clamps it to +3 volts so I don't damage the Pico, and here I've got a binary coded decimal switch where I can choose a divisor or multiplier for the clock. So if I turn this up, if you can hear that, I can choose different divisors. So that's 1 to 1, so I'm getting 1 echo for every external clock signal, and if that's 2, 3, 4, 5, 6, that's 8 and 12, and if I turn that up, we're getting we're almost getting into flutter echo territory there, and going the other way, slightly harder to hear. That's one, and then I can get one echo for every 2 external clock pulses. But if I put it on something like that and just change the incoming frequency, you can hear it's tracking the external clock frequency. And look, don't let anybody tell you that learning the Blinky program isn't useful. I can flash the LED to show what's coming in on here. Haha. Rather than just be driven by an external clock source, I thought, well, why not generate a clock? And then you could drive your sequencer, for example, from the delay rather than the other way around. So that's also quite a good use for the third analog to digital converter input. So connecting a potentiometer up to that, reading the raw clock value, feeding it through a moving average buffer to sort out some jitter, and then calculating a clock BPM in the range of 40 to about 240. And I'm doing this in half BPM steps by multiplying by 2, then dividing by 2, and multiplying the 4095 by 0.4884, which scales it conveniently from 40 to 240 BPM. I'm then calculating a clock frequency and a clock period, and it's this clock period that is going to drive the external clock output. So we'll have a look at that. Quick update of where we're at regarding Pico pinouts. ADC1 I'm using for the clock speed input potentiometer, and GPIO 21, that's physical pin 27, I'm using for the internal clock output. These are the functions that run the clock. So alarm in microseconds is called once during program initialization, and that says we're going to use alarm number 1. We're going to, when the alarm expires, we're going to call this interrupt service routine, and then it arms a timer with a clock period, and during initialization I'm passing in a value of 500,000, which is 60 BPM, so that just kicks the thing off. And thereafter, every time the alarm is fired, is triggered, it arms it again using the global variable of clock period, which is what we saw calculated earlier. So what this is doing is setting up an alarm. It's firing. Every time it fires, it arms again, fires, arms again, and each time it's setting it to the current value of the clock period. And this is a convenient way of being able to vary the clock period, because I can use the potentiometer to change the clock period, and then I use the clock period to drive the alarms that trigger the clock output. So let's have a look at what that looks like. This is what those timers generate. If I turn this up, if you look at the BPM figure, it won't go all the way down to 40 BPM, but it's going up. I can select round or half numbers of BPM, beats per minute, all the way up to close to 240. And the figure on the right hand side is the clock period in microseconds, which is what the timer interrupt service routine is looking at each time it's armed. And here we are. So I've got just a resistor in series with an LED just to connected to the output port, and if I vary the potentiometer, this is the clock speed, we can see it varying smoothly from about 40 BPM up to about 240 BPM. And this is the clock output port. I've normaled it to the clock input port, so you can see that the input frequency is being driven by the output clock. So that's a convenient way of kind of clocking the delay from itself. But what if all I want to do is set a delay by turning a knob.